Hello and welcome back. In this last video lecture, we will look at complex numbers as vectors. And the way this works is pretty straightforward. We call the x-axis is going to be the real axis, and the y-axis is going to be the imaginary axis. And when we have a plus bi, I'll come out here to a b, and we can think of this as the vector. Oops, I didn't draw that very straight. Just like that. So this is the vector in the notation that we had previously. We can think of this as the vector AB. And that's all there really is to thinking about complex numbers as vectors. But then we will be able to do a lot with this. We didn't have a chance to get to very much this semester, but it's important to be able to see this very briefly. So let's graph a few of these vectors. So I've got 5 plus 3i, so 1, 2, 3, 4, 5, and 3. So 5 plus 3i will be pointing up here. But if I take 4 minus 4i, so that so again our x coordinate is going to be 4, 1, 2, 3, 4, and our y coordinate is going to be negative 4, 1, 2, 3, 4. So this vector will be pointing down here instead. Negative 6. So when I look at the number negative 6, again, what I can think of this as is negative 6 plus 0i. And negative 6 just means negative 6 in the x direction. So 1, 2, 3, 4, 5, 6. And then 0 in the y direction, in the imaginary direction. So this is just going to be the vector pointing straight out here. And then 5i likewise, I can think of this as 0 plus 5i. So 5i is just going to be pointing in the imaginary direction. 1, 2, 3, 4, 5. So we can graph all of these vectors and everything, and we can think of these things in terms of vectors as well. So when I add complex numbers, it's the same process of adding vectors. So for instance, if I were to add these guys together, if I think about these as vectors, if I think about negative 6 plus 5i, well, when I add vectors together, I draw my parallelogram. And I draw the resultant vector. Maybe I'll do that in red so it's a little bit clearer. If I could draw in a straight line. Just imagine that's a straight line. And the thing is, this is negative 6 plus 5i, right? Because we've got negative 6 in this direction and 5i up. So as I add complex numbers, it is the same thing as adding vectors. And we can draw all of these pictures. So if I wanted to add say this vector pointing straight up and this vector over here, again I can add my parallelogram just like I normally would, and I can draw the resultant vector, the sum of those guys, and we can go through and we can check the mathematics. Everything works out. Complex numbers are essentially just vectors in 2 dimensions, which makes them really nice. Now, because they are vectors, we can describe them in perhaps a slightly different way as well. So here I've got the vector x plus yi, and this just means I've come out x and I've gone up y, and this is going to be this vector right here. So as I write this, there's a couple things to notice. One is that I can also talk about the length of a vector. And the length of this vector, again, we've got our triangle right here. And this is a right-angled triangle. So this length is x, this height is y. So r, if I solve for that with the Pythagorean theorem, is going to be x squared plus y squared, but that will be r squared, so I take the square root. And there you go. So the length of this vector is going to be x squared plus y squared, or the square root of that. This angle in here as well, I can give this in terms of x and y as well. Again, this length is x, this length is y. So if I take the tangent of that angle, it's going to be the opposite, which is y, divided by the adjacent, which is x. So I can solve for these guys quite easily as well. Okay, so I can find r and theta given x and y. Can I go in reverse? If you give me a vector and you tell me how long it is and what angle it's pointing at, could I figure out x and y? Well, absolutely. Because I know that the sine of theta is going to be the opposite over the adjacent. So I can solve for y as y is equal to r sine theta. Likewise with x, I can use the cosine. So cosine of theta is going to be equal to x over r. So that means that x is simply going to be r cosine theta. And that means that my original complex number with x's and y's in it, I can rewrite that x plus yi. So I can rewrite. Let me write this over a little bit because I'll need to do a little bit with this. So if I write x plus yi, well, x is just going to be r cosine theta plus, and then y is going to be r sine theta times I. And what you'll notice is that both of these have a factor of r in there. So if I pull that out, I can write this as r cosine theta plus, and again, because I don't want you to think that I'm taking the sine of theta I, I'm going to put the I out front. So r times cosine theta plus I sine theta. And every complex number I can rewrite in terms of sines and cosines. And there's where trigonometry comes into complex numbers. So this is called the polar form of a complex number. Essentially, this gives everything in terms of circles, where you can refer to, okay, how far away from the origin you are, and then at what angle are you as you rotate around. So let's go through some examples where we take complex numbers and we convert it to polar form and back. So rectangular form is again the a plus bi. And this is going to be quite simple. Converting things to rectangular form is normally easier than going backwards. So here I have 2 times cosine of 45 degrees plus I sine 45 degrees. So I can turn cosine of 45 degrees and sine of 45 degrees into regular numbers first. There's going to be 2 times, well, cosine of 45 and the sine of 45. This is where cosine and sine are the exact same, and they are both square root of 2 over 2. Okay, so far so good. I've just turned everything into numbers, and now I just need to distribute my 2. 2 times the square root of 2 over 2. Well, the 2's cancel, and I'll get the square root of 2. Also, 2 times I square root of 2 over 2. The 2's cancel, and I'll get I square root of 2. And that's all it is. Converting something into rectangular form, you take away the sines and cosines and write them as numbers. Cosine of 0 and the sine of 0. So it's going to be 10. The cosine of a 0-degree angle, again, when we think about graphing cosine starts at 1. So cosine of a 0-degree angle is 1. The sine of a 0-degree angle, the sine starts at 0 and then starts oscillating. So sine of 0 is in fact 0. So then simplifying this, anything times 0 is just 0. So this is just going to be 10. 10 times 1. If I really am trying to be pedantic, this would be 10 plus 0i if I need to have that in there. But just 10 works. So again, we're just converting sines and cosines into regular numbers and then plugging everything in. Cosine of 172 and sine of 172, this is something that, this is not one of our special angles, this is not something that we know, so this would be just something that I would plug into, for instance, Desmos. So if I want 6 times the cosine of 172 plus so that's going to be negative 5.94 if I just round that to two decimal places. Negative 5.9. What did I say? 4. And then the second one, I'll have 6 times the sine of 172. And that's going to be 0.84 plus I times, I'll do it in the other order, plus 0.84 times I. So again, I just distributed the 6 and took 6 times the cosine and then 6 times the sine, and that's what we get. Going backwards is maybe just slightly harder, but ultimately it's not too difficult. So what we need in the formula for polar form, I need to know r and I need to know theta, which I have my formulas for right here. R is just going to be the square root of x squared plus y squared, and theta, I'll have to solve for that in terms of the tangent. So here, r is going to be the square root of 1 squared plus 1 squared. X is 1 and y is 1. So that's just going to be the square root of 2. And the tangent of the angle that's going to go in there is going to be 1 divided by 1, which is 1. And one thing to notice is that if I graph this, 1, 1 is going to be about right there. And if I'm looking for something where the tangent is 1, this is one of our special angles, and that's the angle that is 45 degrees. So this was pretty straightforward. R is the square root of 2 times the cosine of 45 degrees plus I times the sine of 45 degrees. Cool. It isn't always this simple, so let me pull this off. So let's take R, and that's going to be negative 3 squared plus 4 squared, and I need to take the square root of that. Well, negative 3 squared is 9, 4 squared is 16, so this is going to be the square root of 25, which is 5. And then the tangent of theta is going to be y divided by that. So it's going to be negative 4/3. And when I come over to Desmos and I take the inverse tangent, oops, I need to get rid of that. Take the inverse tangent of negative 4/3. I get a negative 53 degree angle. Which, when I think about this, I'm going to be at negative 3, so 1, 2, 3, and positive 4. 1, 2, 3, 4. Well, a negative 53 degree angle is going to be down here, right? Because we're negative. But I want the positive number. So the question is, how do I turn this negative angle, this negative angle into this positive angle? Well, the tangent repeats itself every 180 degrees. So I'm just going to take negative 53 and add 180 degrees to it to get 127. And this is the angle that I will plug into here. And I'll do that in the next short video.